Okay, so two flasks P and Q contain an ideal gas and are connected with a tube, you can see it here, of negligible volume. So negligible volume compared with that volume and that volume. Compared to that of the flasks. The volume of P is twice the volume of Q. You can see this looks bigger, it's twice the size of Q. P is held at a temperature of 200 Kelvin and Q is held at a temperature of 400 Kelvin. What is the ratio of mass of gas in P with mass of gas in Q? Now, I will help you to calculate this value, but before we do, we can almost have a good guess on this. You see, if there is a tube here that connects these two, so the molecules inside here can move freely between this tube, if the temperature would be the same, but it's not in this case, but if the temperature would be the same and this has twice the volume, then the mass of the molecules in P would be twice the molecule of this. Therefore, this ratio would be 2. That is not an option here. Now, if the temperature here is 400, that is twice as much as 200. Then they will move much more faster inside here. So that means that they will more likely go in this direction than compared in this direction. Because with a higher temperature, you need fewer molecules to have the same pressure. Therefore, we know that there will be even fewer molecules here if the temperature is higher here. So instead of twice, there will be more than twice. Well, maybe 4 or 8 times as much. Well, the answer is if that is twice, then it would be twice as many here because of the reason of temperature. Twice as many because the volume is twice. So twice and twice is 4 times. But let me show you that we can calculate it also. So we will use the ideal gas law. PV is equals to nRT. And they are asking for the ratio of mass. And mass has with the number of moles to do. So with more moles, we have more mass. Therefore, we need to solve for N. So PV over RT like this. And if I want number of moles in P divided with number of moles in Q, then we can write it as P, VP, RTP over P in Q times V in Q divided by R times T in Q. So we have a PVRT over here, and I have a small p over everywhere here. So you see it's in the container P, and then a small q here because it's in a container Q. R is a constant, so it doesn't depend on that, of course, here. Okay, let's see what we do have. Pressure P. It doesn't say, but if the two containers is connected with a tube, the pressure will be the same in both of them. So I will just call it P. Multiplied with volume of container P. Well, that is twice the volume of container Q. So I will just call it 2V. Divided with temperature P. That is, P is held in 200 Kelvin. Divided with pressure of Q. It's the same as the pressure of P, so I'm just calling it P here. Multiply with the volume of Q, that is just V. 2V means twice as of V. Divided with temperature of Q, that was 400, so 400 here. And now you realize that we can cancel away P, we can cancel away V. And eventually I will have 2 over 200 times 400 here. And the 400 divided with 200 goes 2 times, and then we have 2 here, so it will be a 4. And 4 is option C. Just like we could almost argued without any numbers and without calculations. Okay, thank you.